Yeah, hello guys, welcome back. I'm your friend Insect. So today we are going to know the polynomial factorization.
When we first learned algebra together, we started factoring polynomials, especially quadratics. We recognized that an expression like x squared could be written as x times x. We also recognized that a polynomial like 3x squared plus 4x, that in this situation, both terms had the common factor of x, and you could factor that out. And so you could rewrite this as x times 3x plus 4. And we also learned to do fancier things. We learned to factor things like x squared plus 7x plus 12. We were able to say, hey, what two numbers would add up to 7? And if I were to multiply them, I get 12. And in those early videos, we show why that works. We say, well, 3 and 4. So maybe this can be factored as x plus 3 times x plus 4. If this is unfamiliar to you, I encourage you to go review that in some of the introductory factoring quadratics on Khan Academy. It should be a review at this point in your journey. We also looked at things like differences of squares. X squared minus 9. Say, hey, that's x squared minus 3 squared. So we could factor that as x plus 3 times x minus 3. And we looked at other types of quadratics. Now, as we go deeper into our algebra journeys, we're going to build on this to factor higher degree polynomials. Third degree, fourth degree, fifth degree, which will be very useful in your mathematical careers. But we're going to start doing it by really looking at some of the structure, some of the patterns that we've seen in introductory algebra. For example, let's say someone walks up to you on the street and says, can you factor x to the third plus 7x squared plus 12x? Well, at first you might say, oh, this is a third degree polynomial. That seems kind of intimidating, until you realize, hey, all of these terms have the common factor x. So if I factor that out, then it becomes x times x squared plus 7x plus 12. And then this is exactly what we saw over here. So we could rewrite all of this as x times x plus 3 times x plus 4. So we're going to see that we might be able to do some simple factoring like this, and even factoring multiple times. We might also start to appreciate structure that brings us back to some of what we saw in our introductory algebra. So for example, you might see something like this, where once again, someone walks up to you on the street and says, hey, you factor this, a to the fourth power plus 7a squared plus 12. And at first you're like, wow, there's a fourth power here. What do I do? Until you say, well, what if I were to rewrite this as a squared squared plus 7a squared plus 12. And now this a squared is looking an awful lot like this x over here. If this were an x, then this would be x squared. If this were an x, then this would just be an x. And then these expressions would be the same. So when I factor it, everywhere I see an x, I could replace with an a squared. So I could factor this out, really looking at the same structure we have here as a squared plus 3 times a squared plus 4. Now, I'm going really fast through this. This is really the introductory video, the overview video. Don't worry if this is a little bit much too fast. This is really just to give you a sense of things. Later in this unit, we're going to dig deeper into each of these cases. But just to give you a sense of where we're going, I'll give you another example that builds off of what you likely saw.
Okay, when I saw this, I start to realize that one thing. Which is there has a general idea for simplification, like here. If you got a complex equation, what you could do is to find out how it is composed. Then you use your old analogy to solve that kind of problem. For example, x to the fourth power, you didn't know it, right? But you didn't know that x squared plus 7x plus 12, how to solve that kind of equation or expression. Sorry, that's an expression. Then you do that kind of thing. After that, you replace the x with the a squared or a to the 2 power. Then you get the final answer right in here
in your introductory algebra learning. So building off of the structure here, if someone were to walk up to you, again, a lot of people are walking up to you, and say, factor 4x to the 6th minus 9y to the 4th. Well, at first, this looks quite intimidating until you realize that, hey, I could write both of these as squares. I could write this first one as 2x to the 3rd squared minus, and I could write this second term as 3y squared squared. And now this is just a difference of squares. So it'd be 2x to the 3rd plus 3y squared times 2x to the 3rd minus 3y squared. squared. We'll also see things like this where we're going to be factoring multiple times. So once again, someone walks up to you in the street and they say you're a very popular person. Someone walks up to you on the street and says, factor x to the fourth minus y to the fourth. Well, based on what we just saw, you could realize that this is the same thing as x squared squared minus y squared squared. And you say, okay, this is a difference of squares, just like this was a difference of squares. So it's going to be the sum of x squared and y squared, x squared plus y squared, times the difference of them, x squared minus y squared. Now this is fun because this is too a difference of squares. So we can rewrite this whole thing as, I'll rewrite this first part, x squared plus y squared. And then we could factor this as a difference of squares, just as we factored this up here, and we get x plus y times x minus y. So I'll leave you there. I've just bombarded you.
So basically, only in this way, complex the problem can be solved with easy steps. Otherwise, you have to memorize a lot of stupid formulas. I mean, that was stupid. First one, you cannot remember all those formulas because we are at some point general people because we got limited memory. Right? But that doesn't mean something. That doesn't mean anything, you know. Most of the people, they all have limited memory, but some of them could make something big, but others couldn't. Why? Here's the difference. The approach. They take different approaches to solve problems. For those genius, when they look into a problem, what they saw is a bunch of small sub-problems, and they could very easily to solve the big problem by solve those small problems. But for other people, they cannot say how that big problem was composed. So they feel very hard. They feel like, whoa, that question was too hard. I cannot solve it, but that's not true. The only thing that you can do is you cannot split that big question into a bunch of small questions. That's the difference between you and the genius, okay?
You with a bunch of information, but this is really just to get you warmed up. In this video, we're going to dig a little bit deeper into our knowledge or our understanding of factoring. Now, factoring is something that we've been doing for many years now. You can go all the way back to when you were thinking about how would I factor the number 12? Well, I could write the number 12 as 3 times 4. I could also write it as 2 times 6. These are all legitimate factors. Or I could try to do a prime factorization of 12, where I'm trying to write it as the product of, you could view it as its most basic constituents, which would be the prime numbers. And so we've done stuff like, well, 12 can be expressed as 2 times 6. 2 is prime, but then 6 can be expressed as 2 times 3. And so 12 can be expressed as 2 times 2 times 3, which we see right over here. This is all review, and this would be a prime factorization. And we saw an analog when we first learned it in Algebra 1. In Algebra 1, we learn things like, and sometimes this might be in a Math 1 class or even in a pre-algebra class, you'll learn things like, hey, how do I factor x squared plus 6x? And you might recognize that, hey, x squared could be rewritten as x times x, and 6x, that really just means 6 times x. And so both of them have x as a factor, and so we might want to factor that out. And so we could rewrite this entire expression as x times x plus 6. What we just did is we factored out these x's that I am circling in blue. So in general, this idea of factoring, if you're thinking about numbers, you're writing one number as the product of other numbers. If you're thinking about expressions, you're writing an expression as the product of other expressions. Well, now as we go a little bit more advanced into algebra, we're going to start thinking about doing this with higher order expressions. So we've done it with just an x or just an x squared, but now we're going to start thinking about, well, what happens if we have something to the 3rd power, 4th power, 6th power, 10th power, 100th power? But it's really the same ideas. And we could start with monomials, which is a fancy word for just a single term. So let's say I had something like 6x to the 7th. What are the different ways that I could factor this? Pause this video and think about it. Can I express this as the product of 2 other things? Well, I could rewrite this as this is being equal to 2x to the 3rd times what? Well, let's see. What do I have to multiply 2 by to get to 6? I have to multiply it by 3. And what do I have to multiply x to the third by to get to x to the 7th? I could multiply it times 3x to the 4th. Notice 2 times 3 is 6. X to the third times x to the 4th is x to the 7th. We add exponents when we're multiplying things with the same base. But this isn't the only way to factor. Just as we saw that 3 times 4 wasn't the only way to factor 12, you could also express this as maybe being equal to x to the 6th times what? Well, we would still have to multiply by 6 then, and then we'd have to multiply by another x. So we could write this as x to the 6th times 6x. So there's oftentimes multiple ways to factor a higher degree monomial like this. And there is also an analog to doing something like a prime factorization. When you're trying to really rewrite this expression as a product of its simplest parts. How would you do that for 6x to the 7th? Well, you could rewrite that. You could say 6x to the 7th. Well, that's equal to, we could think about the 6 first. We know that the prime factorization of 6 is 2 times 3. 2 times 3. And then x to the 7th is just 7x's multiplied by each other. So times x times x times x times x times x. How many is that? That's 5, 6, and 7. And so some of what we were doing when I said 2x to the third, what we really thought about is, okay, I had a 2, and then I had x times x times x. And then what do I have to multiply that? Well, I have to multiply that by 3x to the 4th. And as we will see, being able to think about monomials in this way will be useful for factoring higher degree things that aren't monomials, things that are binomials, trinomials, or polynomials in general. And we'll do that in future videos.
All right. Let's say the first chapter is that factoring monomial. By saying that, what is a monomial? Well, it's just an expression with let's say one single item in an expression. For example, 4x squared or 6x to the 100 power. That's also it.
Find the greatest common factor of these monomials. Now, the greatest common factor of anything is the largest factor that's divisible into both, if we're talking about just pure numbers, into both numbers, or in this case, into both monomials. Now, we have to be a little bit careful when we talk about greatest in the context of algebraic expressions like this, because it's greatest from the point of view that it includes the most factors of each of these monomials. It's not necessarily the greatest possible number, because maybe some of these variables could take on negative values. Maybe they're taking on values less than 1. So if you square it, it's actually going to become a smaller number. But I think, without getting too much into the weeds there, I think if we just kind of run through the process of it, you'll understand it a little bit better. So to find the greatest common factor, let's just essentially break down each of these numbers into what we could call their prime factorization, but it's kind of a combination of the prime factorization of the numeric parts of the number, plus essentially the factorization of the variable parts. So if we wanted to write 10, we could say, or if we were to write 10cd squared, we can rewrite that as the product of the prime factors of 10. The prime factorization of 10 is just 2 times 5. Those are both prime numbers. So 10 can be broken down as 2 times 5. C can only be broken down by c.
Okay, here he just said a word called prime numbers. Let me write it down. Okay, prime numbers. When he said that, that means that number cannot be divided anymore. It's a small. It's the unite for a multiplication or something like that. So yeah, that's it.
We don't know anything else that c can be broken into. So c, so 2 times 5 times c. But then the d squared can be rewritten as d times d. D times d. This is what I mean by writing this monomial essentially as the product of its constituents. For the numeric part of it, the constituents are the prime factors. And for the rest of it, we're just kind of expanding out the exponents. Now let's do that for 25c to the third d squared. So 25 right here, that's 5 times 5. So this is equal to 5 times 5. And then c to the third, that's times c times c times c. And then d squared times d squared. D squared is times d times d. So what's their greatest common factor in this context? Well, they both have at least one 5. They both have at least one 5. Then they both have at least one c over here. So let's just take up one of the c's right over there. And then they both have two d's. They both have two d's. So the greatest common factor in this context, the greatest common factor of these two monomials is going to be the factors that they have in common. So it's going to be equal to this 5 times, we only have one c in common, times, and we have two d's in common, times d times d. So this is equal to 5cd squared. And so 5d squared, we can kind of view it as the greatest, but I'll put that in quotes where, depending on whether c is negative or positive and d is greater than or less than 0. But this is the greatest common factor of these two monomials. It's divisible into both of them, and it uses the most factors possible.
Taking common factor from binomial, taking common factor from trinomial. So by watching such two videos, at least we could know two things. What is a binomial? What is a trinomial, right?
So we're told to factor the polynomial below by its greatest common monomial factor. So what does that mean? So we have these two terms, and I want to figure out their greatest common monomial factor. And then I want to express this with that greatest common monomial factor factored out. So how can we tackle it? Well, one way to start is I can look at just the constant terms. I can look at, or not the constants, the coefficients, I should say. So I have the 8 and the 12. And I can say, well, what is just the greatest common factor of 8 and 12? The GCF of 8 and 12. And there are a lot of common factors of 8 and 12. They're both divisible by 1. They're both divisible by 2. They're both divisible by 4. But the greatest of their common factors is going to be 4. So that is equal to 4. So let me just leave that there.
Okay, so to get such a, let's say, greatest common factor for two numbers, what you could do is, first step is to find out all those prime factors that number could have. For example, here 1, 2, 4 for the 8, and 1, 2, 4, 6 for the 12. Then we found the biggest one that both exists in the 8 prime numbers list and 12 prime numbers list. We found that common and greatest number. That would be 4, and we got it.
And then we could think about what is, well, let me actually write it right over here. I'll put a 4 here. And now we can move on to the powers of x. We have an x squared and we have an x. And we could say, what is the largest power of x that is divisible into both x squared and x? Well, that's just going to be x. X squared is clearly divisible by x, and x is clearly divisible by x. But x isn't going to have a larger power of x as a factor. So this is the greatest, you could view this as the greatest common monomial factor of x squared and x. Now we do the same thing for the y's. So we have a y and a y squared. If we think in the same terms, the largest power of y that's divisible into both of these is going to be just y to the first power, or y. And so 4xy is the greatest common monomial factor. And to see that, we can express each of these terms as a product of 4xy and something else. So this first term right over here, so let me pick a color. So this term right over here, we could write as 4xy. That color is hard to see. Let me pick a darker color. We could write this right over here as 4xy times what? And I encourage you to pause the video and think about that. Well, let's see. 4 times what is going to get us to 8? Well, 4 times 2 is going to get us to 8. X times what is going to get us to x squared? Well, x times x is going to get us to x squared. And then y times what is going to get us to y? Well, it's just going to be y. So 4xy times 2x is actually going to give us this first term. So actually, let me just rewrite it a little bit differently. So it's 4xy times 2x is this first term, and you can verify that. 4 times 2 is going to be equal to 8. X times x is equal to x squared, and then you just have the y. Now let's do the same thing with the second term. And I just want to do this to show you that that this is their largest common monomial factor. So the second term, and I'll do this in a slightly different color, do it in blue. I want to write this as the product of 4xy and another monomial. So 4 times what is 12? Well, 4 times 3 is 12. X times what is x? Well, it's just going to be 1, so we don't have to write up times 1 here. And then y times what is y squared? It's going to be y times y is y squared. And you can verify, if you multiply these two, you're going to get 12xy squared. 4 times 3 is 12, you get your x, and then y times y is y squared. So far I've written this exact same expression, but I've taken each of those terms and I factored them into their greatest common monomial factor, and then whatever is left over. And now I can factor the 4xy out. I can actually factor it out. So this is going to be equal to, if I factor the 4xy's out, you could kind of say I undistribute the 4xy. I factor it out. This is going to be equal to 4xy times 2x plus, when I factor 4xy from here, I get the 3y left over. So let's 3y, and we are done. And you can verify it. If you were to go the other way, if you were to distribute.
You know what? To be honest, sometimes I do not know why they want to do this transformation from this form to this form. But I guess that's just a way to simplify the whole expression, so it can have less powers out there. You know, for this one. In this expression, it got somehow the power of 2. But in this expression, you can say all of those parts, they only have 1 as the power position.
We're told to factor 4x to the fourth y minus 8x third y minus 2x squared. So to factor this, we need to figure out what the greatest common factor of each of these terms are. So let me rewrite it. So we have 4x to the fourth y. We have minus 8x to the third y. And then we have minus 2x squared. So in the other videos, we looked at it in terms of breaking it down to its simplest parts. But I think we have enough practice now to be able to do a little bit more of it in our head. So what is the largest number that divides into all of these? When I say number, I'm actually talking about the actual, I guess, coefficients. We have a 4, an 8, a 2. We don't have to worry about the negative signs just yet. And we say, well, the largest common factor of 2, 8, and 4 is 2. That's 2 goes into all of them, and obviously that's the largest number that can go into 2. So that is the largest number that's going to be part of the greatest common factor. So let's write that down. So it's going to be 2. And then what's the greatest, I guess, factor? What's the greatest degree of x that's divisible into all 3 of these? Well, x squared goes into all 3 of these, and obviously that's the greatest degree of x that can be divided into this last term. So x squared is going to be the greatest common x degree in all of them, 2x squared. And then what's the largest degree of y that's divisible into all of them? Well, these two guys are divisible by y, but this guy isn't. So there is no degree of y that's divisible into all of them. So the greatest common factor of all 3 of these guys right here is 2x squared. So what we can do now is we can think about each of these terms as the product of 2x squared and something else. And to figure out something else, we can literally undistribute the 2x squared and say this is the same thing. Or even before we undistribute the 2x squared, we could say, look, 4x to the fourth y is the same thing as 2x squared times 4x to the fourth y over 2x squared, right? If you just multiply this out, you'd get 4xy. Similarly, you could say that 8x to the third y, I'll put the negative out front. You could say that 8x to the third y is the same thing as 2x squared, our greatest common factor, times 8x to the third y over 2x squared. And then finally, 2x squared is the same thing as if we factor out 2x squared. So we have that negative sign out front. We have this negative sign, 2x squared. If we factor out 2x squared, same thing as 2x squared times 2x squared over 2x squared. This is almost silly what I'm doing here, but I'm just showing you that I'm just multiplying and dividing both of these terms by 2x squared. Multiplying and dividing, multiplying and dividing. Here it's trivially simple. This just simplifies to 2x squared right there, or this 2x squared times 1. That simplifies to 1, or maybe I should write it below. That simplifies to 1, but what do these simplify to? So this first term over here, this simplifies to 2x squared times, now you get 4 divided by 2 is 2. X to the fourth divided by x squared is x squared. And then y divided by 1 is just going to be a y. So it's 2x squared times 2x squared y. And then you have minus 2x squared times 8 divided by 2 is 4. X to the third divided by x squared is x. And y divided by 1, you can imagine, is just y. And then finally, of course, you have minus 2x squared times this right here simplifies to 1 times 1. Now, if you were to undistribute 2x squared, if you were to undistribute 2x squared out of the expression, you'd essentially get 2x squared times this term minus this term minus this term, right? If you distribute this out, if you take that out of each of the terms, you're going to get 2x squared times this 2x squared y minus 4xy, and then you have minus 1. And we're done. We're factored the problem. Now, it looks like we did a lot of steps, and the reason why I kind of went through great pains to show you exactly what we're doing is so you know exactly what we're doing. In the future, you might be able to do this a little bit quicker. You might be able to do many of the steps in your head. You might say, okay, let me look at each of these. Well, the biggest coefficient that divides all of these is a 2. So let me factor a 2 out. Well, all of these are divisible by x squared. That's the largest degree of x. Let me factor an x squared out. And this guy doesn't have a y, so I can't factor a y out. So say it's going to be 2x squared times, and what's this guy divided by 2x squared? Well, 4 divided by 2 is 2. X to the fourth divided by x squared is x squared. Y divided by 1, there is no other y degree that we factored out, so it's just going to be y. And then you have minus 8 divided by 2 is 4. X to the third divided by x squared is x. And then you have y divided by, say, 1 is just y. And then you have minus 2 divided by 2 is 1. X squared divided by x squared is 1. So 2x squared divided by 2x squared is just a 1. So in the future, you'll do it more like this, where you kind of just factor it out in your head. But I really want you to understand what we did here. There is no magic. And to realize that there's no magic, you could just use the distributive property to multiply this out again. To multiply it out again, you're going to see that you get exactly this.
Yeah, there has no magic about this. Alright, let's say what we can do here. Factoring higher degree polynomial. I thought we did that before, but why there's another video talking about that?
There are many videos on Khan Academy where we talk about factoring polynomials, but what we're going to do in this video is do a few more examples of factoring higher degree polynomials. So let's start with a little bit of a warm-up. Let's say that we wanted to factor 6x squared plus 9x times x squared minus 4x plus 4. Pause this video and see if you can factor this into the product of even more expressions. All right, now let's do this together. And the way that this might be a little bit different than what you've seen before is this is already partially factored. This polynomial, this higher degree polynomial, is already expressed as the product of two quadratic expressions. But as you might be able to tell, we can factor this further. For example, 6x squared plus 9x, both 6x squared and 9x are divisible by 3x. So let's factor out a 3x here. So this is the same thing as 3x times what is 6x squared? Well, 3 times 2 is 6, and x times x is x squared. And then 3x times what is 9x? Well, 3x times 3 is 9x. And you can verify that if we were to distribute this 3x, you would get 6x squared plus 9x. And then what about this second expression right over here? Can we factor this? Well, you might recognize this as a perfect square. Some of you might have said, hey, I need to come up with two numbers whose product is 4 and whose sum is -4. And you might say, hey, that's -2 and -2. And so this would be x minus 2. We could write x minus 2 squared, or we could write it as x minus 2 times x minus 2. If what I just did is unfamiliar, I encourage you to go back and watch videos on factoring perfect square quadratics and things like that. But there you have it. I think we have factored this as far as we could go. So now let's do a slightly trickier higher degree polynomial. So let's say we wanted to factor x to the third minus 4x squared plus 6x minus 24. And I, just like always, pause this video and see if you can have a go at it. And I'll give you a little bit of a hint. You can factor in this case by grouping. And in some ways,
Yeah, I just really want to do it by myself, but it seems like there has a tech problem here. I feel uncomfortable by using the mouse to draw around on the screen if I have to do a lot of driving. There's a way to solve this out, which is to connect to my another computer, and in that computer, this computer, yeah, I could use the electronic pen. I don't know how to call it. Someone call it a panels, but that's it. It's just a pen. I could use that to drive around in the laptop on the laptop screen. so that we could do it easier. Yeah, I'll do it next time. So in the next time, I'll use that kind of technology or method so that we could be able to solve this expression or simplify this expression by ourselves first, then we continue to watch the video. That's the best way for the mathematics learning. Because in an exam, you won't have a teacher around you that tells you what to do next. You have to do it yourself.
It's a little bit easier than what we've done in the past. Historically, when we've learned factoring by grouping, we've looked at a quadratic, and then we looked at the middle term, the x term of the quadratic, and we broke it up so that we had 4 terms. Here, we already have 4 terms, and see if you can have a go at that. All right, now let's do it together. So you can't always factor a third-degree polynomial by grouping, but sometimes you can, so it's good to look for it. So when we see it written like this, we say, okay, x to the third minus 4x squared, is there a common factor here? Well, yeah, both x to the third and negative 4x squared are divisible by x squared. So what happens if we factor out an x squared? So that's x squared times x minus 4. And what about these second 2 terms? Is there a common factor between 6x and negative 24? Yeah, they're both divisible by 6. So let's factor out a 6 here. So plus 6 times x minus 4. And now you are probably seeing the home stretch where you have something times x minus 4 and then something else times x minus 4. And so you can, sometimes I like to say, undistribute the x minus 4 or factor out the x minus 4. And so this is going to be x minus...
Here's a sentence that we should know. So how to express the meaning of extract one part out for both of the part in an expression. How do we say that? We say factor it out. That's one way. And another way for it is to undistribute x minus 4 from this expression. Yeah, basically we got two way or two methods for expression that's meaning.
Minus 4 times x squared plus 6. And we are done.
We are done. It's also a sentence. Means we have finished something. Factoring using structures. Identifying quadratic patterns.
We're told that we want to factor the following expression, and they ask us which pattern can we use to factor the expression, and u and v are either constant integers or single variable expressions. So we'll do this one together, and then we'll have a few more examples where I'll encourage you to pause the video. So when they're talking about patterns, they're really saying, hey, can we say that some of these can generally form a pattern that matches what we have here, and then we can use that pattern to factor it into one of these forms. What do I mean by that? Well, let's just imagine something like u plus v squared. We've squared binomials in the past. This is going to be equal to u squared plus 2 times the product of these terms, so 2uv, and then plus v squared. Now, when you look at this polynomial right over here, it actually has this form if you look at it carefully. How can it have this form? Well, if we view u squared as 9x to the 8th, then that means that u is, and let me write it as a capital U is equal to 3x to the 4th. Because notice, if you square this, you're going to get 9x to the 8th. So this right over here is u squared. And if we said that v squared is equal to y squared, so if this is capital V squared, then that means that v is equal to y. And then this would have to be 2 times uv, is it? Well, see, if I multiply u times v, I get 3x to the 4th y, and then 2 times that is indeed 6x to the 4th y. So this right over here is 2uv. So notice, this polynomial, this higher degree polynomial, can be expressed in this pattern.
Okay, so here he just said a word called pattern. What you did here is to recognize some patterns in something, right? This kind of thing is called intelligence. You know, in some university, they, instead of saying artificial intelligence certification or kind of things like that, they prefer to say pattern recognize class. So in their mind, they just thought that intelligence is nothing but pattern recognition skills, which means you could find something general from a bunch of things. That's how you show your intelligence to everyone. You can find something basic or common rules inside of a series of things.
which means it can be factored this way. So when they say which pattern can we use to factor this expression, well, I would use the pattern for u plus v squared. So I would go with that choice right over there. Let's do a few more examples. So here, once again, we're told the same thing. We're given a different expression, and they're asking us what pattern can we use to factor the expression. So I have these three terms here. It looks like maybe I can see a perfect square here. Let's see if that works. If this is u squared, then that means that u is going to be equal to 2x to the third power. And if this is v squared, then that means that v is equal to 5. Now, is this equal to 2 times uv? Let's see, 2 times uv would be equal to, well, you're not going to have any y in it, so this is not going to be 2uv. So this actually is not fitting the perfect square pattern, so we could rule this out. And both of these are perfect squares of some form. One just has I guess you say, adding v, the other one is subtracting v. This right over here, if I were to multiply this out, this is going to be equal to, this is a difference of squares, and we've seen this before. This is u squared minus v squared. So you wouldn't have a 3-term polynomial like that, so we could rule that one out. So I would pick that we can't use any of the patterns. Let's do yet another example. And I encourage you, pause the video and see if you can work this one out on your own. So same idea. They want to factor the following expression. And this one essentially has two terms. We have a term here and we have a term here. They both look like they are the square of something, and we have a difference of squares. So this is making me feel pretty good about this pattern, but let's see if that works out. Remember, u plus v times u minus v is equal to u squared minus v squared. So if this is equal to u squared, then that means that capital U is equal to 6x squared. That works. And if this is equal to v squared, well, that means that v is equal to y plus 3. So this is fitting this pattern right over here. And they're just asking us to say what pattern can we use to factor the expression. They're not asking us to actually factor it, so we'll just pick this choice. But once you identify the pattern, it's actually pretty straightforward to factor it. Because if you say this is just going to factor into u plus v times u minus v, well, u plus v is going to be 6x squared plus v plus y plus 3 times u minus v. U is 6x squared. Minus v is minus, we could write minus y plus 3, or we could distribute the negative sign. But either way, this might make it a little bit clearer what we just did. We used the pattern to factor this higher degree polynomial, which is essentially just a difference of squares. Let's do one last example.
Too much examples. Yeah, let's watch one more videos.
In this video, we're going to study geometric series, and to understand that, I'm going to construct a little bit of a table to understand how our money could grow if we keep depositing, let's say $1,000 a year in a bank account. So let's say this is the year, and we're going to think about how much we have at the beginning of the year, and then this is the dollars in our account. And let's say that the bank is always willing to give us 5% per year, which is pretty good. It's very hard to find a bank account that will actually give you 5% growth per year. So that means if you put $100 in at the end of a year or exactly a year later, it'd be $105. If you put $1,000 in a year later, it'd be $1,050. It'd be 5% larger. And so let's say that we want to put $1,000 in per year. And I want to think about, well, what is going to be my balance at the beginning of year 1, at the beginning of year 2, at the beginning of year 3, and then see if we can come up with a general expression for the beginning of year n. So year 1, right at the beginning of the year, I put in $1,000 in the account. That's pretty straightforward. But then what happens in year 2? I'm going to deposit $1,000, but then that original $1,000 that I have would have grown. So I'm going to deposit $1,000, and then the original $1,000 that I put at the beginning of year 1, that is now grown by 5%. Growing by 5% is the same thing as multiplying by 1.05. So this is now going to be plus $1,000 times 1.05. Fairly straightforward. Now what about the beginning of year 3? How much would I have in the bank account right when I've made that year 3 deposit? Pause this video, see if you can figure that out. Well, just like at the beginning of year 2 and the beginning of year 1, we're going to make a $1,000 deposit. But now the money from year 2 has grown by 5%. So this is now going to be $1,000 times 1.05. And then that money that we originally deposited from year 1, that was 1,000 times 1.05 in year 2, that's going to grow by another 5%. 5%. And so this is going to be plus 1,000 times 1.05 times 1.05. We're going by another 5%. Well, we could just rewrite this part right over here as 1.05 squared. So do you see a general pattern that's going to happen here? Well, as you go to year end, in fact, pause the video again and see if you could write a general expression. You're going to have to do a little bit of this dot, dot, dot action in order to do it. But see if you could write a general expression for year end. Well, for year end, you're going to make that original $1,000 at the beginning of year end. And then you're going to have 1,000 times 1.05 for that $1,000 that you deposit at the beginning of year n minus 1. And then this is just going to keep going, and it's going to go all the way to plus $1,000 to times 1.05 to the power of the number of years you've been compounding. So you could view this $1,000 as the one that you put in year one, and then how many years has it compounded? Well, when you go from 1 to 2, you've compounded 1 year. When you go from 1 to 3, you've compounded 2 years. So when we're talking about the beginning of year n, you go up to the exponent that is 1 less than that. And so this is going to be to the n minus 1 power. So what we just did here is we've just constructed each one of these when we're saying, okay, how much money do we have in our bank account at the beginning of year 3? Or how much do we have in our bank account at the beginning of year n? These are geometric series. And now I'll write that word down. Geometric series. Now, just as a little bit of a review, or it might not be a review, it might be a primer, series are related to sequences. And you can really view series as sums of sequences. Sequences, and let me go down a little bit so that we have a little bit more space. A sequence is an ordered list of numbers. A sequence might be something like, well, let's say we have a geometric sequence. In a geometric sequence, each successive term is the previous term times a fixed number. So let's say we start at 2, and every time we multiply by 3. So we'll go from 2. 2 times 3 is 6. 6 times 3 is 18. 18.
All right, this is how they define the geometric series. It's just it's a list, but for each element in that list, if we go further, we go to further step, we're gonna multiply it by a common factor. That's it. So I guess this is today's learning, and I'll see you guys in the next one. Bye.